Okay, the real number system, which of course pretty much covers every type of number that you've looked at so far. There is another number system, the complex number system. Those of you that end up doing Extension 2 Maths will learn about those particular numbers. But the real numbers, as I guess the name suggests, are the ones we deal with in real life. So a couple of ideas. Prime factors. Being able to find the factors of numbers is important. Certainly when it comes to, say, factorising those quadratics. We're looking for two numbers that multiply together to give. So to be able to find a factor quickly can be very handy. So every number, natural number or whole number, can be written as a product of its prime factors. We can break it down. So for example, the number 324, which is not prime, but I could rewrite that as 4 times 81. And actually those numbers aren't prime either, so I could keep going. 4 is 2 squared, 81 is 3 to the power of 4, 2 and 3 are both prime, so there's all our prime factors. And using those prime factors, we can build any number that goes into 324. Another term we use a lot is called highest common factor. Now, if you want to find the highest common factor of two numbers, we get both of those numbers and write it in terms of its prime factors. Then you pull out the common factors. So we'll use 1,176 and 252. Now, 1,176, that's 6 196s. They're not prime. That comes down to be 3 times 2 times 49 times 4. We're getting closer. I end up with 3 times 2 cubed times 7 squared. 252 is a bit quicker. 4 63s, 4 times 9 times 7, 2 squared, 3 squared, and 7. Okay, so how do we find the highest common factor? We pull out the common factors. Now the common factors, when we have, you'll notice in the first one we have 2 cubed, and the second one we have 2 squared, is always the lowest power. Because they don't have 2 cubed in common, they have 2 squared in common. And so it'll be 2 squared, 3 and 7 they have in common, which works out to be 84. Okay. And basically, that's what you're doing in algebra when you factorise. Okay, often happens to be an x you're taking out, not just numbers, but you're pulling out all the common factors in the two ones, and whenever you factorise, you always take out the lowest power. So it's the same sort of idea. Okay, lowest common multiple. We also have something in algebra that's similar to this when we're doing our fractions. Lowest common denominator, we call it. But it's the same sort of idea. So again, we would write the numbers in terms of its prime factors. Then we would write down all the factors without repeating. Or what I said when we were doing the algebra one, algebraic fractions, I said if it's not there, put it down. So let's, we'll do a much smaller one, it'll be a bit quicker this time. 48 and 15. 48 are 16 threes, so we get 2 to the power of 4 times 3. 15 is 3 fives, they're both prime. So the lowest common multiple would be 2 to the power of 4, 3 and 5. This time we need all the factors and we take the highest power if there's 2 in common. In this case, the only common one was 3 and they were both to the power of 1. So 2 to the power of 4 times 3 times 5, we get 240. So as I say, in algebra, that's similar to finding the lowest common denominator when we did that. Divisibility tests are very handy when you're trying to work out, is this number divisible by? What are its factors? Let's see how we go with our divisibility tests without cheating and having a look on the sheet, see who remembers. Well, this is an easy one. How do you know if it's divisible by 2? It's an even number, yeah. Okay, so divisible by 3. Yeah. So if you get all the digits in the number, they should add to also be a multiple of 3. 4. Yes. So you look at the last 2 digits, and if they're divisible by 4, then the whole thing's divisible by 4. Okay, who wants to get in first with this one? 5. Ends in a 5 or a 0. That one's a pretty easy one. 6. Yeah. See, 6, not being a prime number, we can use both the divisibility test for 3 and the divisibility test for 2. Satisfies both. Must be divisible by 6. 7. Very good. So double the last digit, subtract it from the other digits, and the answer should be divisible by 7. 8. Yes, now we go to the last 3 digits. That should be divisible by 8. 9. Yes. This time, some of the digits is divisible by 9. And I guess that is because 9 is 3 squared. So you get multiple of 3, but 3 squared. Anyone want to go for 10? Yeah, I mean, of course. Ends in a 0. And how far did I go? Oh, okay. 11. Okay, here it is. You get the sum of the even position digits, and then you get the sum of the odd position digits. If that sum is the same or differs by a multiple of 11, then the actual number is a multiple of 11. Someone grab a calculator and give me a big number that's divisible by 11, and I'll show you what we mean. Don't keep me in suspense here. 8057. Okay, so we add up all the digits that are in the odd positions. So we've got 1 and 7 makes 8, and 8 makes 16, and 5 makes 21. Now we add up all the numbers that are in the even positions. 0, 3, 0, 7, 10. That differs by 11, so it's divisible by 11. There we go. Let's have a talk a bit about fractions and decimals. So rather than the whole numbers, rather than the integers. Converting recurring decimals into fractions is something I want to look at. Now, a terminating decimal into a fraction is very easy because of our base 10 number system. And we know if it's 0.23, then it's just 23 over 100 and away we go. Very simple. Converting a fraction into a decimal, very easy, because we just know that's the top divided by the bottom. We do the division, you end up with a decimal. But how about these recurring decimals into fractions? Let's do one where we know the answer, so we know if we get this right. Well, at least I hope we know the answer. 0.6 repeater is, of course, 2/3. Now, there's a couple of ways you can do this. First way is to say, oh, well, look, okay, I know this is 0.666, and so on. It goes on forever. So I'll let x equal 0.6 repeater. In other words, x is 0.666, and so on. If I multiply that by 10, I'll get 6.666, and so on. But now I've got simultaneous equations. And so I can actually subtract the repeating part, the bit that's causing the problem. And I get 9x is 6, x is 6 on 9, but hang on, I said x was 0.6 repeater, so therefore 0.6 repeater is 6 on 9, or 2/3. Okay. Well, that was one number repeating. Well, what about two numbers repeating? Still do the same idea. That is, of course, 0.818181818181818181, as long as you like. So we'll let x equal 0.818181818181, and so on. This time I'm not going to multiply by 10 because that'll be no good. I wouldn't be able to subtract the repeating part because if I multiply by 10, I won't get 0.8181818181. I'll get 8.18181818. No good. Got to be the same. So we multiply by 100 and then we get 81.8181818181. The repeating part cancels. We do the subtraction, and there it is. 99x is 81. So it's 81 on 99, which does simplify down to be 9 on 11. So the basic idea seems to be, however many numbers are repeating, that power of 10 is what you multiply by. So if there were 3 numbers repeating, I'd multiply by 10 to the power of 3, which is 1,000, and so on. What about if not all the numbers are repeating? So this is 0.327, but the notation here means the first number that are repeating is 2, the second number is 7. So this is 0.3272727272727272727. All right, we'll use the same idea. So I'll let x equal 0.3272727272727. Now, if I multiply by 10, No good, because I'll get 3.272727, but it won't line up. If I multiply by 100, it will now line up. Okay. So the idea still remains. However many numbers are repeating, there's two numbers repeating there. So I'll multiply by 10 to the power of the number repeating. When I do the subtraction, I get something unusual, because we don't normally see decimals in fractions. So this one, x, is 32.4 on 99, but I can easily fix that up. I'll multiply top and bottom by 10, and then I've got 324 on 990. And we get 18 on 55. Okay, that's what mere mortals do. There's just a much quicker way. Remember, maths is about picking up on patterns. Here we go. Let's go back to it. 0.6 repeater, that first one. I know that's going to be 6 because it's the 6 that's recurring over 9 because there's one number recurring. So I'm going to write 9 down. And there's my fraction, 6 on 9. 0.6 repeater is 6 on 9. 0.5 repeater, 5 on 9. 0.4 repeater, 4 on 9. 0.3 repeater, 3 on 9. And so on and so on. So that's 2/3. 2 digits, I'll use the same idea. 81 on the top because it's 81 that is recurring. Now there are two numbers recurring, so I'm going to use 2 9s. And by 2 9s, I don't mean 18. I mean I'm going to write 2 9s down, 99. 81 on 99. There's the answer. Simplifies down. So using the same idea, if I had 0.7134 repeater, where 713 and 4 are all repeating, so 0.7134, 7134, 7134, 7134. The answer would be 7134, because they're the numbers that are repeating, over 9999, because there are 4 numbers repeating. If you don't believe me, put it in your calculator, you'll see I am correct. Aha, there's one person who doesn't believe me. Okay, right. That does simplify down to be 2378 on 333. That is just so much quicker than solving it by simultaneous equations. If we understand the pattern, we understand the maths behind it, bang, I can just write the answer down. What about this one? There is a pattern there to be had. You might not pick up on it straight away, but I can also just write this answer down. Only the 2 and 7 are repeating. So, on the top of the fraction, I put 324. Why 324 and not 327? Well, it's 327, but I'm going to subtract the number that's not repeating. The number that's not repeating is 3. So 327 minus 3 is 324. That goes on the top of the fraction. Bottom of the fraction, I'll put 990. Why do I do that? There are 2 numbers repeating, so I put down 2 9s. There is one number not repeating, so I put down 1 0. Now, obviously, I put the 0 at the end of the number, because if I put the 0 at the front of the number, it doesn't change the number. Yeah? So, number of 9s is however many numbers are recurring. Number of 0s is how many numbers are not recurring. And so there is our 18 on 55. So now they can ask me any question they like. I can just write the answer down. 0.1096 with only the 9 and 6 repeating. So 0.109696969696969696. On the top of the fraction we'll go 1086. That's 1096 minus the 10 or 10 that's not repeating. And then on the bottom of the fraction 9900. 2 numbers are repeating, so I put down 2 9s. 2 numbers are not repeating, so I put down 2 zeros. I'll guarantee if you go to your calculator, that will give you 0.109696969696, however long your calculator screen is. Simplifies down, by the way, 181 on 1650. You see, the way they're going to answer the question in a test is they're not going to say, find this by using simultaneous equations. They're simply going to say, convert this to a decimal. Or, sorry, other way around. Convert this to a fraction. Bang. Just write the answer down. You got it. Save yourself a lot of time. Okay.